like today, after like the two talks we had previously about the company and about algorithms, today I want to give a little introduction on the implementation. So the structure is first, I mean, it is a huge question how we build a quantum computer. So first we need to like define a little bit a tackable challenge we can do in 30 minutes. Then I introduce a little bit the methodology, and then I can talk about single qubits, about multiple qubits, and a little bit about what we want to do differently as a company. So when I mean, considering the title, there are many things I could talk about, and this is like building a quantum computer is like a huge set of challenges, and there's like this part about algorithms, which really makes use of the quantumness for problem solving, which Andres already talked about, and there's a big field of how to fabricate the processors, like a little image here. That's how close I get to fabrication. Then there's the topic of setting up a very cold environment, which our technology needs, which you can see on the right. This is the system which cools down to approximately 10 millikelvin. And then there's a lot of work to characterize, calibrate, and run the algorithms, which includes like a huge set of expertise in understanding of the physics and electronics and in software. And then you need to do all this considering like noise mitigation, and you want to have the right degree of control. And then you need to manage all this huge effort and very unforeseeable project. And then of course you need a good team for this. So to really reach any reason, any meaningful degree of detail, any sensible insight I can talk to you, I can explain you. I want to maybe find a little challenge, little question we can answer in 30 minutes. And the question I want to answer is basically how to implement this Ising Hamiltonian you can see here, which you already saw in Andres' presentation. So this is a Hamiltonian describing basically a two-state system, relatively easy, simple version of it, where you have like the Pauli matrices that describe the two-state system in these two terms and how they interact with each other only in this single way of ZZ interaction. And basically the question is now how we can implement this. And this is actually also the main part of my job at Qilimanjaro. So this talk is about hardware, but actually in the theory team, so I'm trying to do this connection between hardware and theory, and I think it's pretty cool. And yeah, I want to share how this is done with you. So about the methodology. First, there's several things we need to consider. For individual qubits, maybe you've heard like the DiVincenzo criteria for qubits, but this is like the version without gates because we do quantum annealing. But also, for gate-based system, we also need a two-state quantum system. We need to be able to prepare it in a desired initial state, so we can basically know where we start our calculation. We need to decouple multiple qubits because individual qubits are not very interesting. They're not able to do any meaningful calculation. We want to measure the state of the qubits in the system then, and this needs to be done all relatively free of noise and decoherence. So it means that we need to be able to maintain like the quantum nature of the system for for time which is sufficient to do a meaningful calculation. And then we need to do all this also in a way which scales to a large number, so we can reach like a powerful quantum computer. And the last 3 points are in gray, because I'm not going to talk about this in this talk. What we additionally need for annealing is that we need to, when you think of this two-state system as a double well potential, you want to be able to adjust the depth, so basically the tunneling probability of one state to the other, and you want to tilt it, so you want to be able to favor one of the final states. And you also want relatively strong qubit interaction, which enables like basically the qubits to interact in a way which enables like annealing protocols, which are useful. And so there like some degree of frustration with like also more qubits, not only like the closest neighbors. And I want to like briefly introduce like this process which you're following. Actually, we could mention this is called circuit quantum electrodynamics. Basically, this is part of this field. So, and it's basically the process of engineering like a coherent quantum system, which I think is pretty amazing that we can do this. And this is basically based on like electrical circuits in superconducting conditions. And the phenomenon of superconductivity is like a phenomenon which is like macroscopic, which means like if you construct a circuit from it, you're still having many Cooper pairs, but they behave in a collective way. And you're able to represent the system, even it's like consisting of many quantum particles. And usually in quantum physics, you think of few quantum systems. This Cooper pairs, which are like pairs of electrons, behave in this collective way. So this is just to keep in mind when you think of like this very big systems, and like relatively big in compared to other quantum systems. And this electrical circuit is then built up in this way of working with like basically simplified electrical elements, which basically possess only like the main characteristic without a general geometry. And this is like a capacitor, a inductor, like a linear inductor, and voltage source. And we also gonna later introduce a nonlinear inductor, which is called Josephson junction, which it's where basically the real important part of this starts. And to study this, we need to like basically formulate Hamiltonian, which is done very similar like classical electrodynamics. So this is basically very similar like writing a Hamiltonian for classical circuit. So it reminds me always like the courses of analytical mechanics, where you from conservation laws in this system can derive the Hamiltonian. And then you can quantize this Hamiltonian. This is just done by promoting the quantum, like the operator to quantum operators. So you ensure that the computation relations are hold, and then you have a quantum Hamiltonian. Actually, that's actually not a big step. And then you need to do this to study this in a numerical way. These Hamiltonians are usually not analytically solvable, so we need to study this in a numerical way, and this basically answering the question, how can we write this as a matrix, which is quite tedious. step and gonna save you from this, but I'm gonna just show you the fun part, the results of this. But still, I thought it's interesting to see like the process, and then this Hamiltonian will then be diagonalized, and we can obtain a spectrum from it, which means like the set of eigenvalues. And then in this talk, especially, and in general, often we want to think about the resulting two-level system, which correspond to this superconducting circuit. So if we want to build a qubit, we can basically start from like maybe one of the simplest circuits you can think of, also in classical electrodynamics, which is just the circuit of inductance and the capacitance. And when you do all this process, which I basically sketched out previously, then you find this spectrum, which means like which is basically a harmonic oscillator. So we have many states which are separated with the same energy difference from like 0 to 1, the same difference as to 1 to 2, and so on. So you're not able to address the transition from 0 to 1 only without affecting the other transitions, or there are like so many photons of the same energy traveling around that you're not able to currently like do any operation on it. So what you actually need is an anharmonic oscillator, which is done by introducing like this new element, which I already like teased before, which is this element consisting of like a superconducting part, insulator, and another superconducting part. It's actually really much looking like this. And the interesting thing is that the wave function, like this collective wave function of the circuit, is overlapping basically in this region, and this results in a tunnel probability of the Cooper pairs, which results then in a nonlinear current relationship, and this means that we have basically a nonlinear inductor, which means that we found this quantum anharmonic oscillator, which is basically a transform, which is already true qubit, used by many people. And here you can see that the different states are like separated with energy differences, which vary from the different steps in the spectrum. So here you can really address a specific transition, for example, like two states you usually do your computation on. Okay. But I mean, even though Transmon is a qubit, and we actually also at Qilimanjaro we use it for the Quantum Spain project at the Barcelona Supercomputing Center. This is not what we are looking for to do annealing to emulate the spin system, because when you do this process, which I sketched out before, you find this Hamiltonian which has only like the Z term and the X term missing, and there are ways to trick around to find the X term with some controls, but this is you never find like a smooth control of like the X and Z terms, which are required for annealing. And like it's a bit more intuitive explanation is basically that the transmon doesn't have like we call it the Zeeman-light splitting, which means introducing a magnetic field changes basically the sign of the terms, such as a spin 1/2 particle. So this is not a good system to emulate a spin system. So we continue like playing around with this electrical circuits, and like quite some time ago, people found that when you have a circuit consisting of 3 of these Josephson junctions, you have a system where they're like circulating currents, so superconducting currents, which go either like one way or another, or even like superposition of this, which is quite like counterintuitive, but still happening. And So these are qubits which change basically the direction of the current depending on the magnetic field, and this way we have this flip of the sign. And then this is also the qubit we use for our annealing project, which is called Rocket. And to get a bit more into details of this specific qubit we like, is, for example, the large anomalisticity, which you see in the spectrum. So you can see the three lowest energy levels, independence of some control. And you can see that like the separation of 0 to 1 is very different than to 1 to 0, 1 to 2. And this means that you can address this easily, and also like photons traveling around the system is not like randomly hitting transition which matches this this transition energy of the computation. And okay, this is actually kind of formalizing what I've said before, that you have this two lowest states, which depending on the external flux, change the direction of the persistent current, which you can see here in these little drawings. And this means that you can map this easily on this binary spin variables of the annealing Hamiltonian. And we also required like some special degree of control for annealing, which means that you can basically with the two different control fluxes, and this is not like a straightforward relationship due to quantum flux, but with two controls you can control the two terms of the single qubit spin Hamiltonian basically. So this is just as one example. You can see here the potential well for two settings of the external flux. So in one state, and in one setting you have like a single well, and then with some external flux you have the two wells with some low separation, and you can find also intermediate states where this two circulating currents at left and right like is separated up with a different barrier, so with a different tunneling probability. And that's what you want to smoothly control this kind of single qubit Hamiltonian. And then basically that's finishing the part of the single qubit. And furthermore, we want more than just single qubits. And there are different ways of putting this little circuits together. So you can just put like the flux qubit, so this circuit with three of these junctions, nonlinear inductors, just next to each other, and there's some way of interacting. You can have basically share them, have them share a wire. You can put another linear of this Josephson junction at the shared wire, or you can have this lower schemes of basically adding some complexity, which allows us to couple the qubits together in a way which is controllable, so we can control also the coupling term. And this basically we can use also one of these qubits for this. And when you put now the two qubits with the three junctions, here's also like some inductances drawn. Here's another qubit with this inductances, and the coupler, which in this case share the wire, but this is really not making a difference in terms of the physics which is happening. Important is that we have here a nonlinear inductor, the Josephson junction, which means that we can, in this simple example of two qubits, we can already write like a Hamiltonian as we were aiming for. So we have the x term, the z term with the two parameters, and also the coupling, which is dependent on basically at the end all terms are dependent on all the fluxes, because they're like the phenomenon of crosstalk and also quantum crosstalk. So when you really want to have full control of these parameters, then you need to calibrate your circuit. So you need to study what control you need to apply to really have the effect of just applying this loop. So this is quite complicated problem, especially if you want to go to many qubits, but still in like the bare concept, you found this Hamiltonian we are aiming for. And as an example of how to scale this up, there's like this the layout from D-Wave is, I mean, a relatively easy step from what we learned so far. We can basically explain this already with these few concepts. And here you can see that you have also the X and Z terms with the parameters, which can be controlled like either through the main loop of the qubit or through some other additional loop which you add just to add this controllability. And also the coupling terms can then be adjusted by this couplers, which also like always the same idea, drawing some loops, putting some non-linearity in it, and like putting some magnetic field on it to control it. And these are like the subsystem of two flux qubits. And if you want to have more, then you can, in the scheme of D-Wave, you can just extend the wires of the qubits such that they overlap with, I think, 8 qubits are in this drawing. So these qubits can interact with each other, and this interaction can be controlled by this coupling circuit, which sit at the crossing of these qubits. So in this scheme, you already can understand like the basics of the annealing work or layout. And so this was basically the basic of annealing so far, and now I want to explain just a little bit on what makes us special. So we want high quality single qubits with long coherence times, which doesn't really exist so far. We want quantum interactions, which are like make the qubits interact in a way which is which helps us to add some more degree of controllability and complexity to the Hamiltonian. This way enables more powerful algorithms, and we need many qubits, and we need to find the smart schemes of connecting them, which means basically decide which qubits are connected to which other qubits, because to connect every qubit with all the qubits is not possible for many qubits, at least as far as I know. And just as a little outlook, why we are confident that we can build a system with better single qubits, I think I can explain just by looking at this graph, because in the last 20 years, you can see the coherence times here on the log scale increasing like radically, and I marked some key developments. And for us, we're going to base our technology on this capacitively shunted flux qubit, which is one of the longest coherence time and which is suitable to do annealing, as I explained a bit before. And I think, that's basically the physics part of the talk. And then I want to mention that we always have like the need for people to join the project. So we have position for internships, for bachelor master students, and also for theses. We have an industrial PhD, as I do myself, and we have also permanent positions, especially in the hardware team, like doing control and characterization, and the theory team doing applications and algorithms. And then you should not hesitate to ask questions if you're interested in this position. these are the references, and yeah, I can very much recommend the book as already recommended by Andres, which is one of my main references. Thank you. You can, by the way, also ask questions in Spanish. I'm not confident enough to do this talk in Spanish, but you can understand Spanish.
Thank you very much, Chris.
Muchísimas gracias, Chris, por tu exposición. Bueno, como os ha dicho a todos, podéis hacer las preguntas en español porque las va a entender, o las podéis poner por el chat también, como queráis. Habéis visto que en la última presentación ha puesto pues mucha bibliografía. Uno de los libros es el que el otro día comentaron Jan y Andrés, el de Juan José García Ripoll, ¿verdad? Y bueno, pues aparte de ese, pues que es el primero que aparece además.
Yes. I think it's the first like modern textbook on this. There's another textbook which is much older, but if you want like basically a approach, like a book where it really breaks down the topic in like a student level, and you don't need to work your way through all the papers, then it's, I guess, the best text you can find.
Fenomenal, pues todos los invitados o toda la gente que habéis estado viendo esto, que tenéis alguna inquietud, queréis preguntar algo. Mira, alguien... Preguntan por el chat que por qué no se utiliza el tipo de qubit Gatemon que tiene más coherencia. Creo que he leído bien la pregunta. Sí.
I'm not sure. I think G is here. So I don't think it's more coherence, but in this plot, I marked the qubits which are indicated as J, which are the qubits related to the idea of flux qubits, which I showed is the idea we want to use for annealing. So basically the red marked qubits are the ones we want to use for annealing, and the other qubits are usually used for gate-based computing, so probably all the others are not suitable.
Muchas gracias. ¿Alguien más se anima? Tenéis una oportunidad única de hablar con Qilimanjaro, todos los que estáis.
Yo quiero decir que, although in English, I'll say that the hardware-related knowledge is very difficult to find nowadays because, as Chris mentioned, everything is in papers and it's difficult to find. So here you have the opportunity to ask someone who is directly working on this on a daily basis and developing new technology. I have a question for you, Chris, which is with qubits, we have something called crosstalk. Chris, can you explain a little bit what that is and how do you solve it for the case of flux qubits, which is our technology?
So crosstalk means that when you basically apply through this line a current which produces a magnetic field and introduces a magnetic field, and then, for example, in this socket, this magnetic field is also going into the other loops. So we cannot find a layout which only limits this magnetic field really 100% to the place we want to have it to go. So we need to basically study which set of these three controls result in the control we want. So basically, maybe it's like it's basically solving a problem of linear equations in this case, trying to apply the right control to really result in the control we want. This is relatively easy for like classical crosstalk, which I just described. In 2-qubit case, if you want to go to more, that's very difficult. And also there's a phenomenon of quantum crosstalk, which is basically the different elements introduce like a quantum phase, which basically means they influence each other's wave function. And this is also resulting in yeah, in a kind of interaction we want to avoid, or actually we want to have full control of. And this is also like the same kind of studying our knobs we can turn in the lab and what actual control is executed on the system.
Thank you very much, Chris. As Chris said, crosstalk is one of the biggest problems in developing new technology, especially us. And it's real challenges. Challenges like this that they're not explained here, but they're important. They are there, are the ones that we need to solve. And that's why we need all of you, everyone who's interested, to look into the positions and to study masters in this and join this field, because it's constantly evolving and we need to solve a lot of challenges, and we need you, basically.
Exactly. Okay.
Pues muchas gracias por tu respuesta. Bueno, pues no sé si alguien más quiere preguntar algo, tanto por el chat como levantando la mano, que veo que nadie se anima. O...
Have another question? Can you hear me?
Yes.
Okay, so thank you, Chris, for the talk. It was really interesting. And my question is, well, related to D-wave, because I don't know if, are you aware if any quantum algorithm has been proved, tested in the D-wave devices and actually have some, I don't know, quantum supremacy or anything like this?
I don't think there's some quantum supremacy shown in D-wave yet. No,
Okay.
because they don't have long coherence qubits. And I mean, they still have an interesting system, and they do interesting stuff, but quantum supremacy is not there yet.
Mm-hmm. All right. So that's all for my side.
Okay, thank you.
Muchas gracias por tu pregunta, Gonza, y por la respuesta, Chris, desde luego. Pero vuelvo a preguntar lo mismo. Disculpa que sea tan repetitiva, pero no sé cuándo si hay gente que quiere preguntar algo más, por no alargar esto mucho más. Ya sabéis que podéis preguntar en español, en inglés, por escrito o por a viva voz, como acaba de hacer nuestro invitado Gonza.
Y deciros que esta es la última charla. Si en el caso de que, bueno, tenéis el correo de contacto de Chris, os podéis enviar correos, lo que necesitéis. Y ya está, tienes que aprovechar porque mira, aquí lo tenemos, ya
Sí.
queda grabado. Y nada.
Pues sí que es verdad, la verdad es que es una oportunidad única preguntar en directo, porque luego cualquiera que lo vuelva a ver, las dudas ya, bueno, tienen que ser por escrito y no se pueden compartir, y de esta manera, bueno, pues posiblemente la duda se resolvería para todos, o si hubiera más gente con la misma, claro. Pues dicho esto, veo que nadie levanta la mano, veo que nadie pregunta. Si queréis podemos ir dando por finalizada
Creo que sí.
la tercera charla. Bueno, pues muchísimas gracias, Qilimanjaro, a Chris, a Jan y a Andrés por las 3 charlas que nos han explicado cómo se puede construir y cómo se puede trabajar con los qubits, aunque todavía que parecía que hace poco parecía que era como muy lejano, ya parece que se está acercando el futuro, ¿no? Para poder utilizarlos y sacar un máximo rendimiento y resolver problemas complejos, que es la finalidad de todo esto, y en poco tiempo y con un gasto mínimo de energía y de espacio y de dinero, por supuesto. Pues reitero las gracias a Qilimanjaro y a todos los asistentes por vuestra participación todos los días anteriores y todos los que os habéis animado hoy. Y cerramos aquí este ciclo de 3 charlas. Como os han dicho ellos, nuestros 3 compañeros de Qilimanjaro, tenéis sus correos electrónicos en las diapositivas que podréis revisar cuando subamos esta charla, junto con las otras que ya estén en nuestro canal de YouTube, y podéis preguntarle lo que queráis y animaros a intentar hacer con ellos vuestros trabajos de fin de grado, o incluso si habéis terminado de trabajar, porque esto apunta a que tiene muchísimo futuro. Venga, pues muchísimas gracias a todos. y,
Muy bien.
y poco más, que nos vemos en otra ocasión. Cuando queramos podemos volver a ampliar, cuando esto haya avanzado un poquito podemos repetirlo y contar muchas más cosas que seguro que vais a conseguir en un futuro muy próximo.
Claro que sí.
Venga,
Hacer parte nuestra y nada. Hasta la próxima.
hasta la próxima. Muchas gracias a
Hasta la
todos.
próxima. Hasta luego.
Hasta
Oh,
luego.
adiós.
Hasta luego.